Hey everyone, so this is the solution video to Worksheet 6.1. We're going to be talking about exponential functions and logarithmic functions. In number 1, we're going to explore this relationship between exponential and logarithmic functions by keeping in mind this very important property that connects the two. So if we have an exponential expression which tells us that b to the power of some number a is equal to c, it has to be the case that the log base b, so that same number b, of c is equal to a. So if we have those three values, then we can establish a dual relationship between those two as an exponential or as a logarithmic. So let's start with a. So we're given an exponential relationship. 2 to the power of 3 is equal to 8. Now, this is easier for us to bend our minds around because we kind of understand how exponentiation works. We're basically just multiplying 2 times itself 3 times to get 8. The logarithmic expressions are a little bit less intuitive. So let's break this down. If we're given 2 to the power of 3 is equal to 8, we could, using this relationship that we're given above, we could say, well, this 2, this is our b. This is the base. This 3 is our exponent, which we're just going to call our a, and the 8 represents the c in terms of this part of our expression. So now all we have to do is convert it into a logarithmic expression. So we can do that because we know that the log base b, which in this case is 2, of c, which in this case is 8, has to be equal to the exponent a, which in this case is 3. And that's it. So this would be the logarithmic version of the statement that we have here, 2 to the power of 3 is equal to 8, which implies that the log base 2 of 8 has to be equal to 3. Notice that the value of the log base 2 here is the exponent, that 3. So that's always going to be the case. The log of something is going to be equal to the exponent of the base in a corresponding exponential relationship. All right, so let's keep going here. So I don't think we have to point out the a, b, and the c each time. I think we can see that from above. So in this case, we're going to write, since 5 to the power of negative 3 is equal to 1 over 125, we can write this as a logarithmic expression by saying that the log base, in case our base is 5, and notice that the word base carries over between the two. The base of a log is going to be the exact same number as the exponential base of the exponential version. In this case, it's 5. So the log base 5 of 125 is going to be equal to negative 3, which is our a in this case. So again, just to kind of to drive this into the ground, there's our b, there's our a, here's our c for the exponential, and it translates as there's our b, there's our c, and there's our a in the corresponding logarithmic expression. All right, so let's move on to part C. These are getting pretty easy now. So here we've got the log. The base of our log is the base of the exponential, which in this case is e. The log of, in this case, 1, is going to be equal to the exponent, which in this case is 0. Now the log base e is something that we use quite a bit. It's actually on our calculator. We use it so often that we might be asked to get a value of it. So we actually call the log base e the natural log. So I'll make a note of that. That the log base e, this is the natural log. Or the natural logarithm. And that e is just a constant, and that's Euler's constant. So we're going to use that quite often. Again, it's on your calculator. You've probably used it already. But the notation that we use for the log base e, or the natural logarithm, is going to look more like this. It's the ln. So we can say that the ln of 1 is equal to 0. We'll always remember that, because lots of times you probably will just see it written as the ln, and you'll want to remember that the base of that logarithm is e. Okay, so let's move on to part D. So in part D, now we're going to be given a logarithmic expression and asked to convert it into an exponential. So again, we'll remember the relationship here that base of our logarithm, that's the b, the value that we're taking here, that's the c, and then this, the value of the logarithm, is our exponent a. So if we're going to convert this into an exponential relationship, and this is probably what we're going to spend most of our time doing in problems like this, is understanding the value of a logarithm by thinking of it as an exponential relationship, because it's a little bit more intuitive, the exponential arithmetic involved. So let's write this. So this tells us that our base 5 to the power of a 2 has to be equal to the argument of the logarithm c, which in this case is 25. So that would be the exponential version of this. And I forgot to box this last one. Okay, so now we can move on to part E. And again, we can rewrite this very similar to the next one, except here we've got our exponential base, which is the same as our logarithmic base, 25, to the power of 1/2, the value of the logarithm, is equal to the argument of the logarithm, 5. Now this is the exponential version of this, but notice that algebraically we're probably more used to seeing that power of 1/2 as a square root. So the square root of 25 is equal to 5. So be aware of this because we're going to see this again later. Okay. Part F. So here we've got a log, excuse me, and we don't have a base specified here. We call this, when we've just got the log, we call this the common log, or the common logarithm. And again, this is another one that we see quite a bit, and I'll explain why in a second. The implied base here is log base 10. And this would be the log base 10 of 100 is equal to 2. So this is our way of sort of reinterpreting this. So the reason that the log base 10 is something that we use so often is because we, as at least in Western civilization right now, we use a decimal-based number system. So all numbers are composed by powers of 10 based on the position of a number or a digit in the number system. So for example, if we had a number like 2,542, well, each of these digits in this number represents an increasing multiple of a power of 10. So I think it's not much of a stretch for us to think of this as 2,000 plus 500 plus 40 plus 2. That's what that number is. Each of those digits represents 1,000, 100, a 10, and a 1 position. Now each of these numbers can be thought of as a multiple of a power of 10. So 2 is the same as 2 times 10 to the power of 0. 40 is 4 times 10 to the power of 1. 500 is 5 times 10 to the power of 2. And 2,000 is 2 times 10 to the power of 3. So that's why we've got this number system that lends itself to using the common log quite a bit, because it's a log base 10. Babylonians had a 60 number system, so it probably would make more sense for them if they had understood logarithms, or they had been invented then, they would have used the log base 60 as their base for their common log. But I digress, and we can get back to this problem. So let's think about this. So we know that we're dealing with the log base 10 of 100 is equal to 2. So our base is 10, which I've just talked extensively about. And our exponent is going to be 2, and that has to be equal to our argument inside the logarithm of 100. So that's how we could reinterpret this one. So again, if you see a log without an explicit base, the implied base in this case is 10, unless you're in ancient Babylonian, in which case it would be 60. All right, so the last one, G. We've got the ln of E is equal to 1, and now we're going to go ahead and recall that the ln is the log base E. So we're being asked what's the log base E of E. well, we're told it's equal to 1. So in this case, we could go ahead and we could rewrite this as our base e to the power of 1 has to be equal to e. All right. Okay, so that should do it for number 1. And now let's go ahead and move on to number 2. So here we're going to use the skills we've just developed of interpreting logarithmic expressions in an exponential form to help us actually evaluate these. This is a great thing to be able to do in terms of bending your mind out of the value of a logarithm. What does it mean? What does the log of base something of something actually mean value-wise? So let's go ahead and give these a shot. So the log base 3 of 27. So this is going to be equal to something. And we're going to kind of want to think of this as an exponential expression. So again, we've got our b raised to the power of some exponent, which we're trying to find is going to be equal to that c. So maybe it would be a good idea to kind of write it that way in this case. We're looking for this exponent a. So we know that 3, our base, to the power of something is going to be equal to 27. We just need to figure out what that exponent is in this case. Well, let's think about 27. We want to think of 27 if we can write it as 3 to the power of something, as a base of 3, or maybe some sort of multiple of 3's. Well, 27 is pretty convenient for us to think that, well, 27, that's going to be equal to 3 times 3. So 3 times 3 is 9. If we multiplied it by 3 again, that would definitely give us 27. So 27 can be thought of as 3 cubed. With that in mind, we can write this as the log base 3, because that's the base of our exponent, of 27 has to be equal to 3. And I'm not going to write this every time, but we can say that since 3 cubed is equal to 27. But 3 was really the number that we were after here, the value of the logarithm. All right, so let's try this next one. So 2, or log base 2 of 32 is equal to what? Well, let's give it an exponential form. So 2 to the power of what is going to be equal to 32? Well, let's see if we can express 32 as a power of 2. So 32. Well, if we take 2 times 2, that's going to give us 4. Times 2 again is going to give us 8. Times 2 again is going to give us 16. Times 2 again will give us 32. So if we multiply 2 times itself 5 times, we're going to get 32. So this is going to work out really nicely for us. So we can rewrite 32 as 2 to the power of 5. So there's the exponent that we were after. That's the value of the log here. So we can say that the log base 2 of 32 is equal to 5. And again, this is since 2 to the power of 5 is equal to 32. So again, the value of the logarithm is just that exponent of our base that gives us the value in the argument slot. Okay, so now we'll move on to part C. Part C, we can rewrite this. So we want to ask ourselves 36 to the power of what is going to give us 36? Well, this is somewhat trivial. We know that 36 is just 36 to the power of 1. So the number is going to be 1, that the value of our logarithm is. So we can rewrite this by saying that the log base 36 of 36 is just equal to 1. This gives us a nice little rule. If you haven't talked about it already, it gets outlined in the section on properties of logarithms. For any log base that we're allowed, so any positive number b, we can say that the log base b of that base b, as long as those two are the same, is always going to be equal to 1. because we're essentially raising that base to the power of 1 to get the number back. So this is a rule or a property of logs that we have. We can use that. So for part D, let's start off by writing this as an exponential expression to sort of frame our question. So we're wondering 6 to the power of what is going to give us 1 over 36. All right, we're going to have to take a slightly different approach to figure this one out. We're not going to be able to just keep multiplying 6 by itself over and over again to get 1 over 36. It's just not going to work out that way. So we're going to have to get a little creative. So let's think about the number 1 over 36 and how we can connect it to a base of 6. Well, 1 over 36, we know that 36 is 6 squared. So maybe we could write it as 1 over 6 squared. And 1 over a number raised to some power, in this case 1 over 6 squared, we can rewrite using properties of exponents as 6 to the power of negative 2. And now we're done. We've found the exponent associated with our base 6 that gives us 1 over 36. So we can say that the log base 6 of 1/36 has to be equal to negative 2, because that's the power of 6 that gives us 1 over 36. Okay, so let's check out this next one. So we're asked to find the log of 0.01. All right, so the first thing that we're going to want to remember here is that since we're being given a logarithm with no base, that our base for the common log is going to be equal to 10. So we're going to use that in working out this problem. So if we wanted to rewrite this as an exponential, we could say that 10 to the power of what is going to give us 0.01. Well, again, let's see if we can think of 0.01 in terms of some power of a base 10. Well, 0.01 is 1/100th. So this is the same as 1 divided by 100. And it should seem like it's going to work now, because we can write 100 as 10 squared, and we can write 1 over 10 squared as 10 to the power of negative 2. And there we've got the value that we're looking for. So we can rewrite this as saying that the common log of 0.01 of 1/100th is going to be equal to negative 2. So very much like the last one, because we were after that exponent right there, the exponent of our base 10. Okay, so next we've got the log base 6 of 1. What is that equal to? So we ask ourselves, well, 6 to the power of what is equal to 1? Well, in this case, it doesn't really matter what the base is. Any base raised to the power of 0 is going to give us 1. So in this case, we could use that fact, and we can say, well, 1 is the same as 6 to the power of 0, and that's going to be the value that we're after. So we can say that the log base 6 of 1 is equal to 0. This brings us to another rule or property of logarithms that we can sort of generalize here. The log of any base b, or the log with any base b, of 1 is always going to be equal to 0. So we can pick any base that we're allowed to, so any number greater than 0 as our base, take the log of 1 using it, and it's always going to be 0. So we can use this as a rule. Okay, last one. So we've got the log base 13 of the square root of 13. If we rewrite this as an exponential, we've got 13 to the power of is equal to the square root of 13. So we think about root 13. Well, one way that we can rewrite the square root of 13 is 13 to the power of 1/2. And that's what we're after, that exponent of 13. So our last problem, the log base 13 of the square root of 13 is just going to be equal to 1/2. Okay, so lots of practice with these, but a really important skill to be able to do, and also just really important conceptually in terms of understanding what logarithms mean. So I hope this worked out all right for y'all, and I will see you in the next video.